Welcome to Module 18 of the Six Sigma Institute's Lean Six Sigma Certification Curriculum, which follows both the Council for Six Sigma Certification and the International Association for Six Sigma Certification Bodies of Knowledge. A full copy of the Council for Six Sigma Certification's Book of Knowledge can be downloaded from the course description section for free. In this module, we will be discussing normal probability distributions. This module will take approximately 60 minutes to complete. At the end of the module, there will be a 5-question quiz on the topics discussed, which you can complete on your own at any time. You will also find several Six Sigma tools that you can download, including a z-score calculator and a normal curve calculator, both of which are Excel files. Descriptive statistics are numbers used to describe a set of data. Given a set of data about employees in a company, for example, someone might say, over 50% of the employees work in sales or marketing departments, or 86% of the employees live in the same zip code that the office is located in. These are descriptive statistics because they simply discuss the nature of the data at hand, averages, means, and even the standard deviations associated with that data are all descriptive in nature. Inferential statistics involve calculations and resulting numbers that draw more general conclusions from the data. For example, if you have data about a sample of 150 employees in a city, not all the employees from a single business, but random employees from different companies, you might be able to use inferential statistics to draw conclusions about all of the working individuals in the city based on the data in your sample. While descriptive statistics can relate to population data or sample data, inferential statistics are used to draw conclusions about the population from sample data. If you randomly select 20 people from an overall population and record their height, then the mean of the recorded heights is a descriptive statistic about the sample size. Descriptive statistics about the sample are used in calculations for inferential statistics about a population. Probability is the likelihood that a certain event or outcome will occur given a specific set of data or a specific action. In this section, we are going to discuss probability distributions. When discussing basic probability, we talk about outcomes and events. The outcome is the result of one trial. If you flip the coin once, or you randomly select a single item from the sample. The event is a specific outcome or outcomes. The coin coming up heads is an event. A person measuring 5 feet tall is an event if you are talking about selecting from a population or sample. Here we can see the formula used for calculating basic probability, which is the probability is equal to the number of events that are defined as the outcome divided by the total number of events. In the case of the coin, there are 2 possible events or outcomes that can occur when you flip it. Only one of those events is coming up heads, therefore 1/2 or 50%. In the case of rolling a 6-sided die, there are 6 possible events. The probability of rolling any particular number is 1/6 or 16.7%. The probability of rolling any one of 2 particular numbers, however, is 2/6 or 33%. If we have 23 marbles in a bag, 3 red, 5 black, 8 blue, and 4 green, what is the probability of pulling out a green marble? That probability is the number of green marbles in the bag, 4, divided by the total number of marbles in the bag, 20, which gives you 20% chance of pulling out a green marble. What is the chance of pulling out a black or blue marble? Well, we would add the number of black and blue together and divide by 20, giving us 65% chance. In a Six Sigma setting, you are not dealing with marbles in bags, but the ideas of probability are somewhat similar. If a process produces 100 products an hour and two of those products are defective, the probability of receiving a defective product within that hour is 2 out of 100 or 2%. However, it is rare that a team or business unit would review all 100 products that were produced during that hour in order to know that 2 out of 100 were defective. That information is also only useful for stating probabilities with relation to that particular hour of output. Given that the sample wouldn't be random, instead, Six Sigma experts randomly sample the population of all outputs of a process for a certain amount of time. They create descriptive statistics about that sample and use the descriptive statistics to further study and understand the nature of the data they are working with. Once they know the nature of the data, they can then work with probability distributions and curves to determine probability via calculations and statistical analysis. Before moving forward with probability distributions, it is important to understand histograms. Histograms are another graphical analysis tool. Technically, histograms are bar charts where each bar or bin corresponds to a data range. Data points within a sample or population are divided between the bins and are graphed accordingly. Histograms are used to analyze continuous or variable data that is finite in nature or comes from a population sampling. Histograms help Six Sigma experts understand how the spread or distribution of the data is shaped and where the center of that data might be. The center is the average or middle of the data spread, though the mean or median values aren't always located at the center of a histogram. A histogram also shows the range of the data, the variation between the highest value of data set and the lowest value of the data set. Finally, the histogram shape provides information about where the data is concentrated. For many new Six Sigma practitioners, the idea of bins versus frequency can be daunting. Most people create charts with at least two sets of data, a label and a value. But beyond that, it can get confusing, especially when dealing with histograms. So, let us take a moment to discuss them. Let us say that we have a class of 14 students, and they all took the same test. After grading the test, each of the students was given a score between 1 and 5. 2 students received a score of 1, 5 students received a score of 2, 4 students received a score of 3, 2 students received a score of 4, and only 1 student aced the test. We just divide the data into bins, 1 for each of the possible grades, and we provide a count for each of the bins, 2, 5, 4, 2, and 1. This is the frequency. If we chart this data in a column chart without spaces between them, we have a basic histogram. It appears to be slightly skewed to the left, but nevertheless, it is a histogram consisting of bins, of test scores, and the frequency or count of each bin. There are 6 major distributions that you will be dealing with in most Six Sigma projects. The perfect or normal distribution is symmetrical. It appears much like a bell shape in a histogram with the bulk of the data in the middle. Because no process can ever be perfect, you will most likely never see a truly perfect bell curve. Instead, as the result of natural limitations to a process, most of the curves you will see will be skewed either to the left or to the right, much like our last example with the students' test scores. When you are dealing with a measurement that is in control, you will most likely see a uniform distribution, but they can also be caused by data from multiple processes being combined. A bimodal distribution, which has 2 camel humps, is usually as a result of mixing the data from 2 separate processes or from 2 separate shifts on the same process. A multimodal distribution, which will have 3 or more humps, are created by the mixing of data from multiple processes. Naturally, now that we have discussed histograms, it is time that we actually create one using Excel. We will look at creating a histogram manually using the Analysis ToolPak. As we saw in the student scoring example, we need two columns of data. One column will have the bin designations, and the other will have the data points. If we use the example in the book, then in the first column, we will add all of the data points from the sample, and in the second column, we will designate the bins in increments of 5, starting at 10 and going to 75. Once this is done, simply select the Data tab and choose Data Analysis. A dialog will pop up and you can select Histogram, then click OK. A new dialog will then pop up, providing you the input and output options. Under the input options, click the box for the input range and then select the data column. Then hit Enter. Next, click the box for the bin range and select the column that included the bins, and then hit Enter. Select New Worksheet Ply option in the output selection and check the box next to Chart Output. Once the dialog looks like the one pictured here, go ahead and click OK. Excel will now generate a histogram based on the data and the bins that you selected earlier automatically, and it will place that chart along with the bin and frequency table into a new worksheet on the same file. Unfortunately, this graph defaults to a standard column chart with spacing in between the bars, which is what we do not want. With the graph selected, you will see the Design and Format Tools tab above the ribbon. Making sure that you are in the Design option, you will see an option for Quick Layout. When you click on that option, a drop-down appears, giving you a number of layout options to choose from. Choose the layout where the bars are stacked next to each other without any white space in between them. While you can leave it as is, it would not look right to someone who is familiar with quality control, as histograms will have no gaps between the bars. Normal distributions, also called Gaussian distributions, is probably the most important distribution related to continuous data from a statistical analysis standpoint. In this section, we are going to take a closer look at what we consider to be a normal distribution. Because in a perfect normal distribution, 68.26% of all data points fall within plus or minus 1 standard deviation from the mean. Plus or minus 2 standard deviations from the mean indicates the area under the curve that includes 95.46% of the data points, and plus and minus 3 standard deviations from the mean indicates the portion of the curve that covers 99.73% of the data. Less than 1% of all the data will fall under the curve outside of 3 standard deviations on either side. But all distributions, even normal ones, will vary a bit. We have touched on how visual inspection can help you determine whether data is normal or not. But that does not necessarily mean that our data is normal. Remember, everything we do in Six Sigma needs to be verified through statistics, and that even means verifying that our data is normal. To do this, we need to conduct a goodness of fit test, which is most commonly known as the chi-squared. This test will compare our data and bins against what the expected data and bins should be, and will provide us with a p-value. If the p-value is greater than our alpha risk, which in a chi-squared test should be set at 5%, then we accept the null hypothesis, which states that our data is normal. But if the p-value is lower than the alpha risk, we reject the null hypothesis, accepting the alternative, that our data is not normal. In order to conduct a goodness of fit test in Excel, we need to first create a histogram. Since we just created one in the last section, we will continue to use it in order to determine if the data we had was normal. If you already deleted the histogram, then you will need to recreate it. This can be done by adding all of the data points from the sample into the first column and designating the bins in increments of 5, starting at 10 and going to 75 in the second column. Once this is done, select the Data tab and choose Data Analysis. A dialog will pop up and you can select Histogram and click OK. A new dialog will then pop up providing you with the input and output options. Select the data and bins that will form the input, select New Worksheet Ply option in the Output section, and check the box next to Chart Output, and click OK. Once the histogram and table are generated, format it by changing the layout and removing any spaces between the bars. Now we need to go back to our original worksheet, the one with all the data points, and select the Data tab above the ribbon again, and then choose Data Analysis. But this time, instead of selecting Histogram, we will choose the Descriptive Statistics option. A dialog box will appear, and you can choose the same dataset used to create the histogram from the first worksheet and select Grouped by Columns. Once again, select to output the results to a new worksheet ply. Make sure that the box next to the Summary Statistics is checked because we will need these numbers to see our p-value. The default alpha risk is 5%, but you can change that by checking the confidence level and increasing the number to an amount greater than 95%. The sum of the confidence level and alpha risk will always equal 100%. Once you click OK, Excel will automatically generate the descriptive data from the data points we selected. It will provide you with the mean, median, mode, standard deviation, sample variance, skewness, range, sum, and count, among other tidbits of information. For the chi-squared goodness of fit test, you will need to take note of the sample size or count, the same standard deviation, and the sample mean. The sample size is the number of items in the dataset, which was 50 for this example. If you don't remember what the sample size was, you can refer to the count listed in the descriptive statistics. The chi-squared goodness of fit test is actually a hypothesis test. That means that you are testing the data with regards to a null hypothesis and an alternative hypothesis. In the goodness of fit test, the null hypothesis will always mean the data is normal, and the alternative hypothesis will always mean that the data is not normal. If one is not true, then the other one is. In statistical terms, we talk in terms of accepting or rejecting the null hypothesis. If we reject the null, then naturally we accept the alternative. Basically, the chi-squared goodness of fit test takes the number of samples in each bin on the histogram and compares that to the number of samples you might expect to find in each bin given a normal curve. Using the actual number of samples in each bin and the expected number of samples, we can calculate what is called the chi-square statistic in Excel. That number then lets us calculate a p-value. In this case, it is the size of the p-value that lets us decide whether to accept or reject the hypothesis that the data is normal. For the purpose of the chi-squared goodness of fit test, in this situation, if the p-value is greater than 5%, we will accept the null hypothesis that our data is normally distributed. Having already created a histogram via the Analysis ToolPak, you already have access to the observed bin distribution. That information is housed in the data table Excel created when you made the histogram. As long as you have not deleted these worksheets, you should still have all of that data available to you. We can use statistics related to the normal curve to calculate how we might expect bins to behave given the median and standard deviation of our sample. Because mathematical formulations exist for determining the area under the curve, it is possible to determine the area under the curve within a specific bin. Ultimately, that is done by calculating the total area and subtracting the portions. To calculate the CDF in Excel, we go to the worksheet that was created when we did the descriptive statistics, and we copy the bin designations from the first worksheet to column D. Then you will add a total CDF column, column E, and a bin-only CDF column, column F. In order to calculate the CDF, we will use the normal distributions formula. And so in E2, go ahead and enter equals NORMDIST, open parentheses. Next, we need to add the x value, which is found in D2, comma, the mean, which can be found in B3, comma, the standard deviation which can be found in B7, comma, and the word true followed by the closed parenthesis. Hit enter to obtain the CDF for the first bin. Then do the same for each bin, but remember the only variable that will change will be the X value, the first cell after the open parenthesis. Next, in the bin-only CDF column, we start with the same number as the total CDF bins. So, in F2, we enter equals E2, then hit enter. The next calculation will be the total CDF for the bin minus the total CDF for the prior bin. So, in F3, enter equals E3 minus E2, then hit enter. In F4, enter equals E4 minus E3, then hit enter. In F5, enter equals E5 minus E4, then hit enter, and continue this until the end of the column. This basically results in the values in the column representing a percentage of the whole. In the final column, G, we will need to calculate the expected number for each of the bins, and for this we will need that total count. In G1, enter equals F2 asterisk $ B $5, then hit enter. Copy this formula down the column. To calculate the chi-squared statistic, you will use both the expected number of items in each bin and the actual or observed number. The observed number was automatically generated when you created the histogram, so you only need to copy that data from the histogram worksheet and paste it into column H. In column I, we will subtract each observed from the expected and square that number. To do this, select I2 and enter equals open parenthesis G2 minus H2 close parenthesis chevron, that little up arrow that you can get by holding down the shift key and pressing the number 6, then the number 2, since we are squaring the total of the results from the inside of the parenthesis. Do the same thing for each row. Lastly, we take the last calculation and divide it by the expected bins. Sure, we could add that to the last calculation, but to show you how it is done here, we will keep them separate. In J2, enter equals I2 divided by G2. Repeat this calculation down the column. Now we need to sum the total of column J. So, in the first empty cell in column J, J16, enter equals sum, open parenthesis, close parenthesis, then select all of the values in column J and hit enter. The resulting value is our chi-squared statistic. But in order to find the p-value, we also need to calculate the degrees of freedom. The degrees of freedom are equal to the number of bins minus 1 minus the number of calculated perimeters. In this example, we have 14 bins, and the total number of calculated parameters is 2, the mean and the standard deviation. So our degrees of freedom are 14 minus 1 minus 2, which equals 11. Now we can use an Excel formula to calculate the p-value. In J17, enter equals CHI DIST, open parenthesis, J16, the cell which contained the chi-squared statistic, comma, 11, close parenthesis, then hit enter, and Excel will calculate out the p-value. In this example, the p-value should be 0.116 or 11.6%, which is greater than our 5% alpha risk. Since the p-value is greater than the alpha risk, we accept the null hypothesis and declare that our data is normal. Once you verify that your data is normal, you can use many statistical tests to draw conclusions about the data and the population as a whole from your sample. One of the things you can do is use Excel's normal probability functions to draw conclusions about the data. For example, let's assume that the data we've been working with is a sample selection of the weights of boxes in a delivery channel. The 50 samples were taken from the same shipping center over the course of a week and were randomly selected. Given that we know that the data is normal, what is the probability that any package selected from the distribution center will weigh over 50 pounds? In order to find this, we select a cell and enter equals NORMDIST, open parenthesis, 50, which is the value we are testing, comma, 48.778, the mean from the descriptive statistics, comma, 11.444, the standard deviation from the descriptive statistics, comma, false, closed parenthesis. This would calculate the odds of picking up a box that weighs more than 50 pounds. If you had selected true, it would calculate the less than 50 pounds probability.